Yeah.
So
So the streaming will start.
oh, okay. When it starts, then you tell me when to start.
Yeah, I'll do that. Yeah. So streaming has started, and yeah, Raja, we can start now.
Okay. Okay, great. So just some preliminary remarks. The previous two lectures were somewhat general. They were not specific to any work I had done, though toward the end, uh, I did bring up the collaboration with Sanjay Patnagar on closure phase. And we'll have more to say about that in lecture 4. So this lecture, though it will begin with polarized interferometry, will move on to some related themes which are somewhat theoretical and also somewhat personal. In the sense, I found them interesting. I pursued them. I hope you do too. Okay. But let's start with the early days of interferometry with the polarization. At OVRO is the Owens Valley Radio Observatory, which was founded in 1958. And very sensibly, the Caltech people simply imported two of the best radio astronomers from Australia, John Bolton and Gordon Stanley, and they in turn imported other people whom you will see about. So this is the Owens Valley interferometer as it was. So there are these two dishes. I mean, they would be large, except to people who are used to GMRT. They're 90 feet or 27 meters in diameter, but just two dishes, okay? And there is a railway track on which they can be moved. And for polarization, this is what they had. Okay. So none of these modern conveniences of a feed which receives both polarizations and gives you two outputs. They had this rectangular waveguide, which, I mean, waveguide feed. You can see that it'll admit this polarization basically. And that's it. If you wanted some other direction, then you ran this motor till this rotated. Okay. And likewise on the other dish. And equally, when they did spectroscopy, they had a single channel which they would move around at different frequencies. So you can see that radio astronomers today, all over the world, and certainly in GMRT, enjoy luxuries which were completely unheard of in the early days. Nevertheless, there is a paper which I'm going to start with showing you, and it's a very ambitious paper. So these are the three authors who are all, I think, in their early 30s, brought into Caltech by the founders of the observatory. And this is a absolutely general title, The Measurement of Polarization Distributions over Radio Sources, which presumably means that they were one of the early people to write about it. And the abstract is very terse. It just says a method by means of interferometric techniques is described. And then, instead of just sticking to what they had in Owens Valley, they decided to, and this is what you would expect of very theoretically minded people, think of an interferometer where you have arbitrarily polarized antennas. Need not be orthogonal, need not be linear, circular, anything. And of course, having derived this general formula, they discuss some special cases of interest. Now, I wanted to make sure that I was not being RRI chauvinistic in pointing you to this paper, but it is cited by many of the later papers, including the ones that I will put up from the Westerbork group by Bregman, Salt, Hammaker, and so on. But I also went to a site which had a history, more like a bulletin of the observatory. And Marshall Cohen is, one of the towering figures in radio astronomy of that period. Of course, this is what he says. A powerful new method was worked out by our postdocs. And here they are. And then it carries on. Now, there's one thing which is terribly wrong in this thing, that Radhakrishnan only had a BSc, and his doctorate, and that too an honorary one, came only some 40 years later. But you can see that this may still be Caltech chauvinism, but still, I feel better at having checked out these two things. So let's straight away fast forward to the equation which they had. Okay. So the I, Q, U, and V here are now interferometric. Okay. So it means that you have the I, Q, U, V in the sky, and then they are multiplied by a kind of fringe, which depends on the baseline and also where the source is located. Okay. But they have isolated. So all that is in this prefactor K. Okay. And this just tells you how far back we are. In this prefactor K, they even include the rotation of the Earth, which of course is now routinely taken out and you forget about it. In any case, let's focus on this part. Now, the problem which I and Sanjay worked on was really confined to this first line. We had no Q, no U, no V, and we did have general polarization. But I should also tell you what these thetas and phis are. Okay. Phi is nothing but the alpha of the first lecture, which means it's an azimuth of the major axis. But of course, to go to the Poincare sphere, you have to double it. Now, theta is the ellipticity of the first feed, 1 and 2. Okay. Ellipticity is again defined by the ratio of the minor axis to the major axis being tan of omega. So omega only goes up to 45 degrees or pi by 4, and then you double it to get the Poincare sphere. Except the word Poincare sphere doesn't enter into this paper. And in general, there will be an imaginary part. This has a face. Okay. Of course, you can also see that in the case of orthogonal feeds, which is the most familiar one, you will get no response. If you have two orthogonal feeds, you'll get no response to I, right? Because to an unpolarized source, the two orthogonal directions would be unpolarized. Now, I don't intend to delve into this equation much more, except to say that it had a bit of a role in my getting involved in this subject. Okay, so that's a bit of anecdote. So, I joined RRI in 1975, and every now and then Radhakrishna would drop in and either raise some questions or ask us what we were doing. But he never mentioned this, fully well knowing that I was very interested in optics and polarization and all that. But he just didn't mention it. That was his nature. But then he was interested in pulsars at that time. So we had one of these nice summer schools, and I attended a lecture he gave on pulsars. It was in this characteristic non-mathematical style, but it had one equation because he was talking of interstellar dispersion. So he had the dielectric constant, and he wrote 1 minus omega p squared over omega squared on the board. So after the lecture, on the way back, I told him, okay, it looks like you're getting very mathematical. Okay. And then he said, do you know that I derived an equation which occupies 4 lines in the Astrophysical Journal, which one of my co-authors later understood and the other one still doesn't. Anyway, that's what he said. Okay. So then I got a little curious because this visibility has a very definite phase. And clearly, and these are general elliptic polarizations, right? So what do we mean by the zero of phase of a general elliptic polarization? So they must have used some convention in this calculation. And so the next time I had a couple of hours, which was on a railway journey to Chennai, I sat down. It took me a long time to get all these terms right, using a particular convention, which we'll talk about. And so I satisfied myself that this is the particular convention they used. Now, just to tell you that we are not dealing with, pure theoretical physicists, here are a couple of pictures, which are not widely known. I got hold of them through, Roberts was there at Caltech at the same time. In fact, Radhakrishnan and he collaborated on the magnetic field of Jupiter, which again involves polarization. And Gauss again was there at some point, and he's the one who shared this with me. Okay. So this is what people who derive 4 lines in the Astrophysical Journal look like. Now, in any case, you need to assign phases. Now, in practice, this is not a serious problem. The convention, which is followed in the later papers, is that 2 linear feeds are in phase if their superposition gives linear at 45 degrees. So essentially, one of them is along the x-axis and it reaches plus x at the same time that the other one reaches plus y. Now, right and circular in phase is actually more of a convention in some sense. But once you have decided on a preferred x-axis, you could make the convention, which we did, that when these are moving in opposite directions in the xy plane, and we will say they're in phase when their superposition gives linear along x. So they cross along the positive x-axis. Of course, they also cross along the negative x-axis. Okay. But this still leaves open the question of what would you do for a general elliptic field? Okay, I called it the black box equation, and that's not the name I gave it. That's the name which Hammaker, Bregman, and Salt gave it. And I think the reason they called it is there was a little bit of mystery about this equation in later writing on polarization, simply because the authors did not give any derivation. If you look at, that's the only equation in the paper. Well, there are a few other simpler ones applying particular cases of that. But so they just wrote it down. Okay. I mean, now I got interested in a slightly more general question. Instead of having just two antennas and trying to define the relative phase, which we'll come to that. Okay. Suppose you took all the polarization states on the Poincare sphere and you wanted to assign a zero of phase to them, and you would like it to be in some continuous way. After all, Poincare took great trouble to put all the polarization states on the sphere in such a way that any reasonable definition of two neighboring polarization states, I mean, that they look similar, or if you look at the equations defining them, you could take some difference. So you can define a distance, and when two things are close to each other, the polarizations look similar. So you got the topology right, as I said. Now, getting a global phase convention is a luxury as far as radio interferometry is concerned, because they've been managing perfectly well with their existing phase convention. Okay, not completely, by the way, because the IAU convention, we'll come back to the IAU convention for the x-axis and y-axis, which is really north and east. So it runs into some trouble at the celestial pole. But in any case, I got interested in the problem of finding a global phase convention. Okay. And this was, in the late 70s, I guess. So one way of stating the problem is that here's the Poincare sphere projected onto a usual kind of map. Okay. And the challenge is find a phase convention which is without any discontinuity, which means whatever you do for one of these states, what you do for a neighboring state should be close to that. So to state it in completely recreational mathematics terms, maybe if it had been a live lecture, I would have distributed copies of the sheet and asked you to put a dot on each one of them. Of course, you would have to be a little careful to put the dot on the linear polarization, because you have to specify whether it was moving one way or the other way. But let's say you could solve that problem, okay, to mark the zero of phase in a smooth manner. Okay, so let's try. So it turns out that the convention used in the black box equation is what I would call the major axis convention. Okay, so of course, for linear polarization, the major axis is pretty well defined. And then you stick to it for elliptic polarization. And then by continuity, you put the dot for circular polarization, right? So that's what happened. Oops. Where did I go? Yeah. Right. Now, there are two serious problems with this convention. Okay. One is that as you go around the Poincare sphere, remember, this azimuth only changes by 180 degrees going from here to here, even though the coordinate along the equator of the Poincare sphere, which is double of the azimuth, changes by 360 degrees. Okay, so if this is the Greenwich meridian, this is the international date line. Okay, and you can see that by continuity, you go from here to this side of the international date line, or you go to this side of the international date line, and you get a 180-degree phase difference, a discrepancy of pi, purely in the realm of linear polarization. Okay. So that's one problem. And the other serious problem is that, well, let's look at, let me see, left circular at the bottom of the figure. Okay. Depending on how you approach left circular from linear or elliptic, you end up with the dot at a completely different place. Of course, there is no major axis. But so this dot is like the smile on the Cheshire cat. The major axis has disappeared, but the dot remains by continuity. So this is not a good convention. Of course, I don't want to say that this is a very crucial issue in radio interferometry because, you just pick two of them and then this works fine. Okay. And in the case of orthogonal things like linear or circular, you just make a choice. So here is something which I thought was a clever way to do it. Take any elliptic state in general. We know that it can be expressed as a sum of this one, and this time I've got left elliptic on the left circular on the top of the Poincare sphere and right circular at the bottom. But you can express any elliptic state as a sum of this and this. Okay. Now, just take this one, left circular, as your reference, and just throw out the right circular component. Okay. So we will say that this one is in phase with this. Okay. The kind of synchronization. If this projected onto, you take just the component along left circular, and if those two that is in phase with this, then it's fine. And that convention works. Okay. It works almost everywhere. Okay. So in phase with, I have used this simple definition of resolving it into two components and then focusing on one of the components to define the phase. But the almost is important because when you go to right circular, it has zero component along left circular. And worse still, if you go to right circular by continuity, right, then you find that again, you end up with different answers depending on how you approach. So this was a bit discouraging. Okay. So let's come back to that. Okay, later. But right now, let's look at a smaller number of, let's not look globally at the whole thing. Okay. So in the second lecture, we had this, well, even in the first lecture, we had this formula for the interference term. Okay. Which we looked at in two contexts. One is to understand these Fresnel-Arago laws. When will you not get intensity fluctuations as you vary the phase of one of the beams? And that is when this inner product EA dagger EB is zero. But that's in the orthogonal case. But in the case when the two are not orthogonal, this gives, you could try and make this real and positive, in which case you would get the maximum intensity. Okay. So this is one possible definition which works for just two of them. By the way, it's pretty similar to the one that I tried unsuccessfully earlier, which failed at the orthogonal point. Because basically what you're doing when you do EA dagger EB is that you're kind of resolving. Suppose there is a basis EA and the one orthogonal to EA. You're resolving EB along EA, ignoring the orthogonal component, looking at the phase of this, and making that phase zero. Okay. So this is a reasonable definition of two non-orthogonal states being in phase with each other. Of course, I think I confessed in the very first lecture that in my early days in RRI, and in fact, my first 10 years in RRI, I was just, it's not that I had not seen these papers, but I had not understood them. Okay. And this is the PhD work of Pancharatnam, working with C.V. Raman. And he had very good motivations, completely crystal optics motivations for studying the interference of two non-orthogonal beams. And the reason is that in absorbing crystals, the two beams need not be orthogonal. Okay, I'll just leave it at that. And the reason is that the dielectric properties are no longer a Hermitian matrix. So when you diagonalize it, you get non-orthogonal beams. And of course, he was doing experiments. And so he arrived at this reasonable definition of phase difference. Okay. But it's interesting that his paper didn't have any EA dagger or EA, no complex numbers, no matrices. So it's very much it's like reading Stokes. So if you don't mind, I'll read it out to you. We will be guilty of no internal inconsistency if we make the following statement by way of a definition. The phase advance of one polarized beam over another, not necessarily in the same state of polarization, is the amount by which its phase must be retarded relative to the second inordinate intensity resulting from the mutual interference may be a maximum. Same definition, but look at the different way of putting it, right? And in fact, I sometimes wondered, and especially in preparing this, okay, why did he choose this? Now, one thing is, of course, all the papers he had read would be like this, but that's not completely true. The references of this paper include many of the papers which uses matrices, complex numbers, even quantum mechanics. So he was thoroughly familiar with that. But he decided to write in this style. And I think it's also, again, this is conjecture, that whatever he did, even if he gave a very mathematical definition, C.V. Raman would have asked him to give an experimental definition. So anyway, here's this very nice definition, okay? Which is just the definition that E dagger EB is real and positive. And of course, he tells you immediately that it doesn't work for orthogonal vibrations. So we've talked about two polarized beams. So now let's talk about three. Okay, and Pancharatnam did that. But I will first warm up with some particular cases. So this beam with a dot in this place, right, is represented by 1, 0. Okay, so this I'm using a Cartesian basis, x and y, and at t equal to 0, so this exponential factor e raised to minus I omega t is 1. This is where once you give both these complex numbers, then you also have defined the phase. Okay, so this is a linear polarization with an azimuth of 0 conventionally. Here is linear polarization with an azimuth of 60 degrees. Okay, now we could use the analytic definition. Okay, so it's proportional to half and root 3 by 2, which are the horizontal and vertical components. Okay, but I've also chosen the phase, right? Yeah. And I've chosen the phase in such a way that the interference of these two gives the maximum intensity. You can check that algebraically by taking the inner product of these two, and the 0 won't contribute. You'll get half, which is positive and real. But also more intuitively, you can say, okay, I'm going to break this into one component parallel to the x-axis and one perpendicular, and let's forget the perpendicular, because of Fresnel-Arago tell you that, that's not going to enter into the total intensity. Okay, and then you want the projection of this on this to be in phase. So I think the choice of the dot is correct. Okay. Now, similarly, let us compare this one with an azimuth of 60 degrees with one which has an azimuth of 120 degrees. So now the x component will become minus half, the y components remain the same. Okay. And if you check the sign of the dot product, you can see that it's real and positive, because you get a minus 1/4 here, but you get a plus 3/4 here. And again, more intuitively, you project this onto this, and you will see that we have put the dots in the correct place. But the interesting thing happens. So these two are in phase according to a reasonable physical definition, which is usually called the Pancharatnam convention. These two are in phase because of that. But these two are not in phase. Once you project this one onto this, you will get a negative dot product. And you can also see the projection. When this reaches the maximum, this will be on the opposite side. It will be canceling it out. Okay. So let's do one more example. So this is now, so here you get an accumulated phase change of pi when you go around in the Poincare sphere and come back, following the Pancharatnam definition of things being in phase. Now, something similar happens here. So here is the left circular, and I have put the dot on. So the two linear states are exactly the same ones that we used here. I just recycled them. So in this case, again, project, think of this, project this linear onto this circular. So you ignore this component, or I would say project the circular onto the linear if you like. Okay. So you have ensured that the x components are in phase. That's what we've done. Now, we've already ensured that.
Surajit has a question.
Yeah,
Can
sure, Surjit. Do tell me.
Sorry, it's not a question actually. So apparently, some people are not being able to see the cursor.
This is this peculiar problem that my cursor is white on Zoom, but it is black on YouTube.
See.
Beyond. Okay, so maybe I will just use a few more words. And also, if
Yeah.
you think they will see the cursor if I sort of put it across a white thing.
Yeah, you can encourage them to join on Zoom rather than on YouTube.
Yeah, if we have enough Zoom, absolutely.
We do plenty.
Okay, great. Okay, so you notice that the Y component doesn't enter into the picture as far as comparing the phases of this circular vibration and this linear vibration along X are concerned, and they are in phase. Likewise, these two are already in phase. We have checked it. Now let us check the phase difference between this 60-degree azimuth linear and this left circular. So now this circular can be regarded as a superposition of one which is at 60 degrees and one which is at, I think, 150 degrees, right? So now you notice that when this reaches its maximum, the left circular has already passed its maximum, right? So these two are not in phase. And in fact, the phase discrepancy is 30 degrees, if you think about it. Like 30 degrees earlier in phase, well, actually 60 degrees. Yeah. So this would catch it. So here we got a phase discrepancy of pi when we went around the equator of the Poincare sphere. And now we are going 3 points on the Poincare sphere, one right on top, one on the equator, one you move to around 60 degrees along the equator, and then you come back. And now we are getting a phase shift of 60 degrees, right? Now this, not obvious from the pictures, but it is more obvious from the inner products, is exactly the phenomenon we encountered in looking at, Sanjay and I encountered, in looking at closure phases with 3 antennas, okay? Viewed as a mathematical phenomenon, it's just that. So we can do a little philosophy here, or a little mathematics. So in phase width is a relation which is well defined between 2 states of polarization, okay? And the mathematicians like this concept of an equivalence relation. And it has 3 criteria. You have to like yourself. If you translate into human terms, A likes A. And if A likes B, then B should like A, right? So this is called, I think, reflexive, and this is called symmetric. But there is a 3rd criterion, okay, which we know doesn't work, right? Even in human relations. A may like B and B may like C, but very often C does not like A. So it's not transitive. And that is the phenomenon which I think I already told you crops up in different contexts, but the very first to what we know is in these very early papers by Pancharatnam on the propagation of light in crystals, okay? So let me give you a flavor of his work, okay? Because it's completely different from whatever I've said so far, because as I said, there are no matrices, no complex numbers. What the mathematical tool. So if you don't like matrices and you don't like complex numbers, then you'd better brush up on your spherical trigonometry if you want to reach Pancharatnam's papers. Now, time was when all astronomers had to learn spherical trigonometry. In fact, my father had a subject called astronomy in his BA Maths in Loyola College in the 1930s, I think. And it had only spherical trigonometry. There was no astronomy in it. Anyway, so 3 points on a sphere, okay? And the sides are these arcs, which the shortest arcs, right? Called geodesics. And the construction for a geodesic is draw a plane through AC and the center of the sphere, and where it cuts the sphere is this. Likewise, so these are the 3 sides, little a, little b, little c. And usually they're not measured in units of length because the radius of the sphere is not that important. You could take it to be a unit radius. So ABC are also measured as angles, which are subtended at the center of the sphere, okay? Now, there's not any great problem in defining the angles at the vertices, because once you go to a vertex, you can kind of blow up this region. It's almost like a plane. You can take the tangent to this side and the tangent to this side and measure the angle between them. So that's what the angle is. But as you can already see from the kind of fat appearance of this triangle, the sum of the angles is not pi. It's greater than pi. Okay. Now, there are formulae which are the generalizations of the standard plane trigonometric formula. Either how to express little a in terms of little b, little c, capital A, or a by sine A and so on. They're generalizations. So that's not surprising. But there's one formula which has no analog in plane trigonometry. Namely, you have this spherical excess over pi. Okay. And that is the area of this triangle, if it is a unit sphere. Now that is remarkable. Okay. Let me just leave it at that so that, except I can tell an anecdote. I used this, I stated this result to a class which I conducted in Ayuka maybe decades ago. This was for a bunch of students from the Pune University who were taking a course in cosmology. And maybe in a modern course in cosmology, since the universe became flat, then you wouldn't draw spheres. I drew spheres, and I just threw out this remark and gave them a somewhat clumsy analytic proof for a very small region. Okay. And then when I came out, I was going back to NCRA and I ran into Professor Narlikar. Always seems to find the time to at least say hello and exchange a few remarks. So I told him that, I've told these people this beautiful result, but I don't know of a beautiful proof. And in his usual quiet manner, he said, I will send you something. So what he sent is from a book on recreational mathematics by Mangala and him. And it has a truly beautiful proof of this result. So I will point you to that. Okay. So now that you've warmed up with some spherical trigonometry, this is zooming to section 5 of Pancharatnam's paper. He's not exactly dealing with the same problem of comparing A with B, B with C, and C with A, but he's doing a related problem. So he has a beam of polarization C, some point on the Poincare sphere, is decomposed into two beams in states of polarization A and B. And this is, in general, a non-orthogonal decomposition. Okay? Okay? So, but effectively, A will be in phase with C and B will be in phase with C. But then there'll be a phase difference between A and B. Okay? And he gives you a formula, which is pi minus half E prime. Now, if you map his problem onto the problem we've discussed, it essentially becomes the result we stated. Or the result I've not yet stated, actually, that the phase discrepancy going around a spherical triangle is the area, half the area of that triangle. Okay. Of course, this is stated in a slightly different way because he's dealing with a different problem. But so E prime is the area of this triangle. Okay. And let me leave it at that. This is just to give you a flavor. But the other stunning thing is that there's only one property of the Poincare sphere which he uses throughout the paper, but uses like, as a weapon. The only property used is something that we have mentioned, that if you have two states on the Poincare sphere, which are separated by gamma, then they overlap, so to speak. I mean, if one was a polarizer and one was an analyzer, or if one were an incoming electric field and the other was a field, single field, the intensity would be cos squared of gamma by 2. No mention of phase. But of course, if you keep measuring intensities, you can find out phases, right? And that's exactly what he does in his papers. So what I've given you is just a flavor. Okay. But we can just move back quickly and check that this worked in the case that we had. Okay. So here, this triangle, the equator doesn't look like a triangle, but the total area is essentially the area of a hemisphere, which is 2 pi, and half of that is pi. Okay. So the half the solid angle works here. And here we got 60 degrees, which is, I think, 2 pi by 6. Half of that is pi over 6. And that's, if you look at these points on the Poincare sphere, this is the North Pole. And this is somewhere in the Atlantic, I guess. And this is 60 degrees, so I don't know. Maybe somewhere in the... But you work out the area of this, you'll get the right answer. Okay. And the area is quite easy to work out because it's a fraction of a hemisphere. Okay. So this is this result but Pancharatnam just moves on. And this is the result which I told you last time, toward the end of the lecture, was kind of rediscovered in different contexts by people like Bargman and Berry. And of course, I knew about this by the time I went to NCRA. We used it in this context. But having thought about a global phase convention, having failed to find it, I tried to understand it a little more deeply. Okay. So let's try that. So to start with, our polarized beam is described by two complex numbers, okay, 4 parameters. But suppose we fix the intensity, right? So the Z1, Z1 star, Z2, Z2 star. And further, let us separate Z1 and Z2 into P1, Q1 for the real and imaginary parts and P2, Q2 for the imaginary, right? So you have 4 real coordinates, the sum of whose squares is a constant, which you can take to be 1. So this is clearly a unit sphere, right? But it's a unit sphere living in 4 dimensions, but moving around the sphere, you will have 3 degrees of freedom, okay? So it's usually called S3, okay? Now the choice of P and Q is actually meant to point you to the fact that we are really dealing with 2 harmonic oscillators, right? And you could, if you like, you could think of these as the position and momentum of each of the oscillators. Now, given the position and momentum of 2 oscillators, if you wait for 1 period, they both have the same period, right? They'll move. And we know that each one moves in some kind of orbit. So the combined thing also moves in a circle. Okay. So we are living in this S3. We start with a point and it moves in a circle. And now you are varying the phase, right? The overall phase. Of course, if you change the relative phase, these will change. You'll get a different point. But now we are talking about the overall phase. So now this S3 is full of circles. Okay. But so now the question is, the question of putting a dot on each state of polarization now becomes a different question. Can I draw a surface which cuts all these circles once and only once? Right? That would then give you a natural coordinate system. So on the surface, which would be 2-dimensional, which would be a Poincare sphere really, because every state of polarization cuts it once, and then you would have another coordinate. It turns out that it's impossible to do. The way these circles live, well, the circles are S1, okay? So the way these S1s live in S3 is not simple. They're kind of twisted. You cannot draw the surface. Now, I promised you that we will at least enter the 20th century mathematics, but this phenomenon was already known to Clifford in 1873, but the proper maths of it was done by Hope in 1931. So at least we are into some 20th century mathematics, okay? I will not try to actually show this in pictures. I did try in another lecture, and I can either put a reference to that lecture or, I can give more details. So that's as far as phase conventions are concerned. Okay. Now the other convention, which is also gives rise to some interesting problems, is a convention for polarization. Okay. So, you might be interested in the CMB. So polarization, all over the celestial sphere, and linear polarization, I guess. In fact, I couldn't help thinking that when the first CMB map was produced by Kobe, George Smoot told the press that it was like looking at the face of God. So then when the polarized map was produced, I don't know what he would have said, because God had developed whiskers, okay? There were all these lines, double-headed lines. But this is a more familiar situation. This is the polarization of the sunlit sky, okay? So I think I've got the colors approximately right. There's the blue sky, and you have the setting sun, okay? Now, it's well known, and you can check if you carry around your calcite crystal Polaroid, that you have maximum intensity of polarization, in fact, almost 100%, when you're 90 degrees away from the sun, okay? And the physical reason, which is that in a 90-degree scattering, the incoming polarization can be split into two parts, one in the plane of the scattering and one perpendicular to the plane. The one perpendicular to the plane of scattering can now propagate along the new direction, but the one in the plane of scattering in the 90-degree case is actually parallel to that, and it would have to launch in a longitudinal way, which is not possible, okay? So that's the reason why you have maximum polarization here, which falls off as the scattering angle goes away from 90 degrees in either direction. In fact, the scattering is somewhat symmetric between this. But again, going back to our eagle-eyed Frenchmen who carried around calcite crystals, this time it's Arago who noticed that it's not quite like this, okay? If it was exactly the way I described to you, then exactly opposite the sun would be the point where you would again get 0 degree of polarization. But he actually found that the 0 degree of polarization, even close to sunset, was at a point which is above the horizon. It's called the Arago point. So as you move along this meridian, you have linear polarization in the normal direction that you expect from this single scattering argument. But then you have unpolarized light. And then when you cross that point, it actually flips. Now, the reason is already contained when I told you this is single scattering. So to understand things like this Arago point, and there are a couple of more points also, you need to bring in multiple scattering, okay? That's a very non-trivial problem, okay? And this problem was actually tackled by Chandrasekhar, and he has repeatedly said that it's the one that gave him the most pleasure, okay? So for that, you have to read his book on radiative transfer. And I mean, unless you have a mindset as mathematical as Chandrasekhar, it will probably give you the most pain, okay? Right. Of course, it has certain elegance. I mean, he has nonlinear integral equations and so on, and he solves a very general problem. So he actually solved this problem. And let me show you a plot from their paper in Nature. Right? So you certainly can't say. So there are lots of lines here because he did it for all positions of the sun. When I say he did it, he set up these equations, okay? But he had the secretary, and the secretary was also a brilliant numerical analyst. And this is before computers, I think. So she had to grind it all out on a facet machine, or maybe, which incidentally, when I first did my thesis, I also did some things on a facet machine, right? So I'm sure the plots and things are very much due to Donna Albert. In any case, the Arago point, okay, so just look at the thick line, which is when the sun is on the horizon, theta equals 90 degrees, zenith distance 90 degrees, and the Arago point is somewhere here, okay? Now that was fine. But then he said, look, this is a neutral point, but this is where Q flips sign going from here to here. But you can draw an entire curve where Q flips sign, and he called it a neutral line, okay? And the first time I saw this plot, I was completely baffled. What is happening at the center? Sun is in different positions, but nothing strange is happening in the center. And the entire reason is the convention for Q. So the convention for Q, which was adopted by Chandrasekhar and Albert, and they had a good reason for it, because that was adopted by this gentleman called Dorno, who did these measurements. Right? And he adopted, I mean, he had a telescope and a Polaroid and so on, and I guess the natural coordinate system would have been one in which one axis was toward the zenith and one axis was horizontal. So this is not a good coordinate system, okay? Because it's showing you some strange things happening where actually nothing is happening to the underlying polarization field. It is completely smooth here. So then again, one can ask, are there nice coordinate systems for polarization? Okay. It turns out that a linear polarization, you cannot find such a coordinate system. Okay. And there's a theorem. It's called the heavy ball theorem. Now, I couldn't give you a kind of even a hand-waving proof of the earlier theorem we encountered, that you cannot cut all these S1s sitting in S3. But in this case, it's simple enough that I will try and do that. And one will actually find, if you take the so-called IAU convention, okay, where for defining the Stokes parameters, you take the x-axis to the north and the y-axis to the east, okay? That's fine, except at the North Pole and the South Pole if you're doing the whole. Right? So it's not a great convention, but there are 2 points where it fails. And what the theorem tells you is that there are at least 2 such points. Now, I mentioned the name of Kildall here, maybe only familiar to a few people, few of the old-timers in NCRA. So he was a Swedish electrical engineer who was considered a brilliant designer of antennas and feeds. And in fact, the signature feed of GMRT at 330 megahertz, I think, was the original one. It's been replaced now. Was designed by Kildall. It had 2 dipoles, but it had a ring around it. And the ring around it was to, if you have a single dipole, that's terrible, right? I mean, it's highly anisotropic. So putting this ring around it improved the behavior. So, and Kildall, of course, made a living by making antennas. And these are antennas which illuminate a very big solid angle, but not only for radio astronomers, even for communications people. So he definitely needed a convention, how to describe the polarization radiated by his antenna or received by his antenna as a function of direction. So anyway, Kildall visited us, had enjoyable discussions with him. He convinced us to buy one of his feeds, which are still there somewhere. It's a bit too big to. Anyway, the RF group found a different solution. And he also, we also bought a copy of his book, which I would urge you to read. And he has managed to not get rid of the problem, but ensure that the problem occurs only at a single point by merging these 2 points. So let me leave it at that, okay? Now, I again looked at this problem of conventions of polarization, and if you go to elliptic polarizations, it turns out you can have a smooth thing. And this is work with Sridhar. So again, I'm not going to impose it on you, right? Details on request, as in the case of the Poincare sphere plus phase. So instead of talking of a hairy ball, which is the standard way it is described in the American literature, I'm just, for a change, I'm stating the theorem as saying that if you draw the wind everywhere on the earth, there are at least 2 places where there is no wind. The wind is 0. So how does one go about proving such a theorem? It's really recreational mathematics. So you take a walk in a small loop, okay? And at this point, the wind is parallel to your direction. Actually, the loop is so small that the wind is pretty much parallel everywhere, okay? In fact, such a vector field is called parallelizable by the, You define an index, okay? Which means as you walk, you compare the direction of the wind to the direction in which you're walking. So it was 0, and now it's moving in the negative direction, moving more and more in the negative direction. Now it's at 180, and of course comes back to 360, right? So you can define the signed number of turns that a vector makes with respect to your direction of travel around a closed curve, small curve. And this is called the index, and the index is -1 if you traverse this loop counterclockwise. And if you just move the loop around, this is an integer, it can't change, right? The only loophole, sorry, no pun intended, it can change if the loop passes a point where the vector field vanishes. Because if that 0 sits here, you'll have a 180-degree flip of that vector, okay? So clearly, so that is one way of testing for points where the vector field vanishes. Keep moving this loop around and see if the index changes, okay? And the interesting thing is, you can just find 2 positions of the loop. You don't actually have to visit that point, okay? But if these 2 positions of this loop, moving the loop continuously, give you an index which changes, and what I'm going to do is to make the index change by +2, okay? And the way to do that, you think of this as a short loop around the North Pole, and keep expanding the loop till it becomes the equator. then keep shrinking the loop till it becomes a small loop around the South Pole. But looking from the North Pole, it would still look like this, right? I mean, if the whole Earth were transparent. Now you slide the loop back. Don't expand it. Keeping the same size, you slide it back. And now you will see the loop has become a counterclockwise. It has become a clockwise, right? It's essentially you're now looking at the clock from the other side, if you like. And this is a bigger lesson that if you're on a sphere, there's no such thing as inside or outside a closed curve. You can always, what you think could be inside could also be outside. So the index is changed by +2, which is what tells us that you have these two zeros. So I said at the beginning that this would be somewhat personal. And I also said right at the beginning that pursuing some of these problems, which are motivated by radio astronomy, one sometimes encounters interesting mathematics. So by the way, the notion of an index of a vector field goes back to Poincare. Okay, you would guess. And he was actually interested in celestial mechanics. So the vector field was in phase space, and the points where it vanished were equilibrium points. And so he was, he was after bigger game. And of course, he did it in any number of dimensions. Okay, so any talk should end with, like many papers end nowadays, with acknowledgements, but also with a declaration of any conflicting interests, right? So I mentioned various people going along, and, as what the Americans call full disclosure, this is what I have, okay? So, and I've had inputs from all these people, except the one on top. It was, of course, indirect. So you can see this is a kind of directed graph, and there are people, they're related academically, but also genetically, as you can see. So you have C.V. Raman, and the only person who is not related genetically to him in this line, but who was also his favorite research student in the Indian Institute of Science, was G.N. Ramchandran, right? In fact, when the Vice Chancellor of Madras University in 1952 invited C.V. Raman to come and become the Vice Chancellor because he retired from ISC, C.V. Raman said, no, but I have this student who's better than me, G.N. Ramchandran, please take him. And he did, and the rest is history. Okay. But in the Raman Institute period, his favorite student, was Pancharatnam. And with both his graduate student and nephew, same is true of Ramaseshan, who was my thesis supervisor. Same is true of Chandrasekhar. I haven't drawn an arrow here, but I could have, because I heard a lecture by him on polarization effects in liquid crystals. And that seemed an interesting problem to work on. So I worked on it. And of course, the inspiration from here is entirely through his book. Okay. So I've pointed out, and of course, I've drawn a line E, which could be for encouragement or employee, right? Since okay. Maybe I'll leave the last slide on if people want to know more details. And I don't know, something makes me, I have a feeling that I've been giving lectures so long that I just end in, a few minutes to the hour. But anyway.
Thanks, Rajaram. I think the two additional things which you said can be provided on request. Maybe you should provide it to us anyway. We can add it as supplementary material on the page where the slides will be shared.
Sure. But I needed the request because,
yes,
these are papers in which I'm an author. So it's like someone comes to your house, you don't show them your wedding video without asking you. Anyway.
Yeah. We have time for questions.
Great.
People on YouTube can ask in comments, and people on Zoom, please feel free to unmute yourself and ask.
Judges, are the slides being made available on the website? I didn't find the slide for the second
I
talk.
will have
Yeah.
to check with Divya. I'm just standing in for him because he is
But I can
traveling.
tell you. Lecture 1 was put up, and lecture 2 I sent to Divya. I'm sure if I had sent it to Jasjit, he would have put it up. And Divya is,
Lecture 2 is available on YouTube.
No, not YouTube, the slides.
The slides, yeah. The slides will definitely go up.
Yeah,
I'll
they
send
will
them.
all go up.
Yeah. In fact, I can maybe send it directly to Shil Kumar. That might be the most straightforward thing. Yeah.
No, if Divya has it, he'll be back tomorrow morning.
Yeah. Okay, great.
We'll get it set up.
Great. Okay. So that's the slides.
Any questions? Anything from YouTube?
Sorry, Rajaram.
Yes. Why?
Yeah. So, so if I go back to my question in the last time, so if I have like two antennas and then they have different mixing of polarizations because of leakage and all. So then can I say that I have now two different polarization states, even coming from the same source? And then how do I compare them? And it's
No,
same.
I would not say that. I would say before they enter your antennas, if it's a point source, unresolved point source, which gives you a plane wavefront on which the field is completely coherent, right? A point source, the visibility function is 1. Okay?
Yes.
And even the polarized visibility function is the unit. Well, for an unpolarized point source, the polarized visibility function is the unit matrix. Okay. And of course, for a polarized one, it will have all the entries in the Stokes visibility. So I would not say that we are getting two different polarizations from the same source. I would not say that.
If it's a polarized source.
If it's a polarized source, it's still true when I say there is complete coherence over this wavefront. If you like, on the wavefront, I can imagine this ellipse living. And it'll be the same ellipse. It'll be the same ellipse at every point on this wavefront.
Okay. Yeah. No, but sorry, but then, so when I have the leakage, is it not that it is rotating this ellipse differently by the two different feeds, two different sets of feeds?
But now that is something that is in your control, no? You're right. So the way I would, by the way, I should say something about the next lecture, which will actually deal with these issues of leakage and so on. But I can say that now. So when I talk of let us say you have a feed, and now it gives two complex numbers, which are not the same as the input complex numbers because they've been multiplied by some matrix, right? And those two are different. But would you say that, so if you like, the measured polarization could be different at the two? Maybe I know you'll be satisfied with that. The true polarization, before your imperfect system was the same in this extreme case of a point source, right? Even partially polarized point source, not a problem. But the measured polarization would be different. And that is an aberration of your instrument. In optics language, it's an aberration. Yeah.
Right. Now, if I look at the closer phases where I have three antennas and then there will be the same problem we were discussing, right? Three different polarizations.
Absolutely. Whereas, absolutely. You're right. And that's exactly what we worked out. I can put up that paper also. Now that I have a kind of, I will put up other people's papers as well, but I will also put up the one with Sanjay. And anyway, also there's this issue of copyright, but since I think most of them are on the archive, so it should not be a problem.
What we can do is to put links to authorized sources.
That's true, because if something is on the NCRA website, then it shouldn't run into any legal problems.
Yeah. And at least most of the astronomy sources are available on ADS.
I found Stokes on ADS, but then it said no source available. But I also found it on archive.org, so maybe I'll put that link.
Yeah, that is also good. Archive.org had some problems last month. Their servers had crashed. Yeah, but now I think they're back.
And most likely it's a cyber attack by the big publishers.
Yes.
But anyway, and they're also fighting cases in court.
Yes. Okay. Any other questions? I don't see anything on. It says all messages, but it's not showing me the messages. There a way? So I don't see any messages on YouTube. I think we can close here.
Okay.
Yeah.
Okay.
So,
Thanks, everyone.
Thank
And on Monday,
Thank
my
you.
plan is very simply to cover this recent work, last 2 years. It's
Right.
entirely to do with closure quantities for polarization. Okay.
Yeah.
Be hardcore radio astronomy, I guess.
Okay. Thank you. And bye, everyone.
Thank you. Bye.
Bye.